we went into spectral methods. We asked, what can linear algebra give us, right? So what would be the notion of dimensionality reduction using linear methods, right? And then we asked, what can we do when we go beyond to tensors, right? So from linear to multilinear analysis. And that's where higher order moments can give us information about latent variables. So we related that to unsupervised learning. And then we looked into variational inference as a general approach if you want to do unsupervised learning. We also talked about uncertainty quantification and how neural networks tend to be overconfident, and you need better methods like Bayesian methods that can give you better uncertainty quantification and the ability to do better uncertainty sampling. So that was a quick kind of, in the last lecture, an overview of issues there. So I guess we've been talking about neural networks all throughout the class in the sense of, right, when we were doing linear models, we were saying this is too simplistic in practice. For complex data, we want neural networks, right? When we were looking into uncertainty quantification, we said neural networks don't tend to do this well. But we haven't gone into depth on how to study neural networks, right, and what they can and they cannot do. There's a lot of interest in developing theoretical formulations for deep learning, but at the same time, this is extremely complex right now, how we train them in practice, how we frame them. So there isn't a complete theory yet, and it's not even clear what a complete theory would look like. But there's certainly some foundations available, right? There is classical theory in neural networks. So we'll delve into that today. And we'll delve into what are the different kinds of errors, right, that are introduced when we look at estimation. So if you recall, going back to estimation lectures, we talked about bias and variance, right? And we talked about no requirements on the function class. And I think somebody raised the issue even back then, right? Because we were looking at minimizing the mean square error, but we didn't specify in what class of functions are we minimizing this mean square error, right? So there was no requirement of bounded computational complexity. You could have an estimator that could be arbitrarily complex, right? All you worried was how good was that estimation error, right, or kind of statistical error. And that's why we argued that classical estimation theory or statistical theory does not completely resolve practical issues, because in practice we typically have some bounded complexity estimator. By that, what we mean is it's in some limited function class. Right? We can't search arbitrarily over bounded complexity. Right? So typically what that means is if you're using a neural network, you're saying how big is your network, right? How complex are the operations in each unit? So in a sense, that gives you like a bound of running time, right? So that's one way to think about complexity. There are many ways to think about complexity, and that's what we will cover today. Right, so this notion of complexity means, what is it that I'm trying to capture about the data, right? So do I need a network with 1 billion parameters? Do I need a network with 10 parameters? Right? So how do you decide? Of course, all of you have run into these issues, and in most of the cases, you're kind of going into validation data set, you're asking, how well does this network do? You do a sweep of hyperparameters. You do essentially graduate student descent, right? And you somehow come up with an answer, right? But what are some principles behind it? Is there a notion of what captures the complexity for a certain data set, for a certain function class? Right? And that's what we will frame it today. And note that in practice you may not be able to measure this, right? Because it's kind of assuming something you know about the underlying function, which in practice you may not, but it's still good to start with that analysis and ask, if an oracle told you right, about this problem setup and how complex is the function, can I then reason about what kind of neural network I need, right? So think about, your image classifier, right? So you're going from images, that is pixels, to some categories, as a simple example. In this case, right, how complex is this, right? We don't know. What is the true underlying function? I mean, it's there in our brains, right? But we don't know how complex it is. But suppose an oracle told you how complex it is, right? And you cannot possibly capture the full complexity, but you want some small network to approximate it. How good is that approximation? Right? So that's what we want to analyze. Right? So there is some true underlying function, right, that correctly classifies, right, or classifies, right, may not be correctly, that classifies all the images, right? But then that's in our brain, right? So, but then if you're trying to fit that to a neural network, right, how bad is the approximation error? But of course, in practice, we don't just care about approximation error, we care about estimation error too, right? So this is the classical statistical theory. We already kind of discussed some aspects of it. When we talk about sample complexity, when we say with just finite number of samples, how different is your loss function on these, right, samples versus population, right? That's talking about estimation error. When we were talking about estimation of moments, right, even just a covariance matrix, right? We were talking about, or mean or covariance. When we have only finite number of samples, you won't get a true estimate, right? There is an error. And so that goes back to the tools you thought about in the statistical inference part of the class. But then we can put the two together and we can say that's the overall error. Right, so, when you think about error, right, in estimation and approximation, so we can, as I said, break it down into two parts. There's approximation error, and then there is estimation. Right, and we are thinking of the setup where, there is some function, right, f of x, right, that goes from, say, x is some vector in some d dimensions. And you want to be able to estimate this function, right? But if you also have only finite number of samples, right? So in the supervised setting, we have, right, pairs of samples. So here, right, f of x typically represents, right, the there's also some error, right? So it's not just f of x, there's also some noise as well. So that's the model we have, and we have many samples for our training. Right, so there are IID pairs which are drawn according to that distribution. Right, so there's some distribution of noise. There's of course some distribution of input, and then you see the output y. Right, so this is the standard setup. And once we have this, we want to now be able to provide an estimate for the function f. So as I said before, if the function is something like our image classifier in our brains, that's some unbounded complexity, right? We cannot estimate it perfectly, even if we had infinite samples, right? And that's that error that we make is called approximation error. Say I have some neural network of just k nodes or k neurons, right? I can't possibly estimate f correctly. I'll make an error even if I have infinite samples, and that's called approximation right? So the estimation error is what happens after you also account for approximation error, right? So you're only comparing between what happens at infinite samples versus finite samples, right? So think of it as, this f of x is the oracle, right? So some oracle tells you this is f of x, so which means in practice I never know what it is. But for sake of analysis, I have this. And so we're going to make some approximation error. And this, right, this whole thing is the set of hypotheses, which I'll denote by using H. So this means all the possible classifiers you can express. So say you look at some set of neural networks with a fixed size, what is all possible classifiers you can express with that? That set, we call it H, right? And this one here will be the one with the minimum error, right? So you don't want to pick something here that has worse error to the oracle. So is that clear in this hypothesis class? The one that has the minimum error with infinite number of samples to the oracle. I picked that one. Right, but then this, so usually I think in the notations we'll use, we'll call it H star, right? So this, so we'll incur an approximation error, right, between this. And then the next one will be what we call an estimation error, which compares it with this, right, H star. So, and we'll call this estimator HERM because this will be the empirical risk minimizer. Because all we have is samples. Based on this, I can come up with what is my empirical risk, right? And then I can minimize that. Because the idea is I'm not just given samples, I'm also given some loss function. Like loss function tells me, right, how off is my estimator, right? So let's call it, my estimator is H at, so usually it's at, right? So, and then I want to compare, right, this estimator with my y. So loss function like kind of essentially looks at, right, how different is my estimate from what I observe. So on training data, I can compare the two. And that's why this is supervised, right? You need to be able to, you need to have the label as well as the sample. And so that's what the loss function gives me. And I can just minimize this empirical risk, right? And typically you can think of this empirical risk as we call it F. So say for any estimator I can just call it H. Usually it's sum of the errors, right? So simple one is just 0 on the error. I just count the number of times I gave the wrong answer. If it's a classifier, y is just one of finite number of classes. I can just count how many errors I make, right? So that's a simple 0 on error. I can of course think of square errors, which is what we've done in the estimation theory. So I can come up with any kinds of loss functions, and in the simple IID setting, I can just sum them up, right? So in that simple setting, I just look at how many number of errors I made in the 0, 1 case. Or in the square error, I just look at the average. But that doesn't have to be the case in general formulation. But typical cases, we look at average error. And so empirical error could be the average, could be something more complicated, right? And the one that minimizes this empirical error, right, in this hypothesis clause, we call it ERM, empirical risk minimizer. And so the idea is that's the one that has the least estimation error, right? So, so I want to be able to go for the one with least estimation error. Is that clear? So that's estimation error, right? So, and the idea is you want to be able to look into both the approximation error and the estimation error. Right? So, you know, for instance, if you're only kind of focused on making the estimation error to be small, but your approximation error is huge, in the end, you don't have a good classifier or a good estimator, right? So, so you need to be able to think about both, and that's why that's that hyperparameter search, right? A model design aspect. You know, should I even use a neural network? Maybe not, right? In some scenarios. So it's very important to be able to make that decision. So it's the balance between the two. And also in practice, you know, even though not a lot of theory is known for it, there's one more error. Right, so what do you think, what other error is there in addition to what we discussed? Can you guess?
Optimization.
Exactly, right, so the optimization algorithm we use itself will have errors, right? Because this is assuming you can go to the global optimal solution of this. You know, if it's convex, we know immediately how to do. If it's non-convex, we pretend we know how to do, right? So, but yeah, there's no guarantee, right? So you can arrive at additional errors, and hence, you know, there's kind of like a series of different errors we incur when we are trying to do supervised learning. You know, the nice thing we showed with, of course, matrix methods and tensor methods is, even though it's non-convex, right, you can reason about the errors you make, right? And if you assume subconditions are met, in fact, you have global optimality. And that's why those are nicer. But in general, again, right, we may not have it, and we should keep it in mind. And some of the latest theory papers in deep learning are reasoning about, you know, when can we get to global optimal solution? Can we reduce this error, and how so and why? Can discuss it briefly towards the end of this class. Any questions so far? Right, so, you know, before we get to neural networks and all the complex situations, we can just simply ask, what do we do for just linear regression? As I said, always first start simple, right? Before we make things complicated. And in this case, you know, we look at, say, there is x and y, right? And you know, I want to fit like an arbitrary function f of x to a linear model, right? So that would be a linear model. So I have some weights, and I'm just like kind of looking at inner products of the weights with x. I mean, ignore the bias, right? Like plus, you know, you can also have plus a constant, but you can always absorb that constant by putting a constant here to x. So just for simplicity, I will, you know, just assume you have that form, because you can always give a constant input as an x and absorb that term. Is that clear? Because typically you would have seen also, right, another constant value, but I will ignore that. And right, and the idea is like the overall error I want to express in terms of squared laws. Right? So this is continuous. You know, so far when we were discussing this, I was mostly talking about the classification setting, right? If it was 0 and loss, that was classification. But here, if y is continuous, I can think about, right, discrete, continuous values. So sorry, let me make this now y itself, right? Because there's also the noise still. I mean, f of x is what is the true underlying one. There's also noise, but in practice, I can only kind of, I need to incorporate both, right? So let me do this as y. So just to kind of see what's the notation. Oh yeah. Right, so this is the loss, right? So if I have now, in the perfect scenario, right, I have infinite number of samples, I look at my expected loss, right? So, and that's the population loss, right? So I'm looking at expectation on both x and y. So this is the Bayesian setting, right? So also this is the Bayesian risk because I'm also averaging over x. And so this is now the loss function for a certain choice of weights, right? Linear regression weights, population level. So this is population level loss, right? So now I can break it down into two parts. Right, so how should I break it down? So when we did like estimation and detection theory, right, so what we were asking was, right, for the Bayesian setting, what is the optimal estimator that minimizes the Bayesian risk? Right, so what's the map estimator? So in case of of the Bayesian setting, the one that's the base optimal, if you recall, is the one where we have expectation of y. Right? So this is the one that is base optimal. Right? So this is essentially my f of x. Right? And the thing is, this linear regression may not be this base optimal estimator, right? I mean, in general, there's no reason for this to be linear, right? Unless you assume something about y. Unless y is actually generated, right, by a linear model plus noise, right? That won't be true. In general, this is different. And that's why we'll just break it down into two parts. We'll just add and subtract, right, this term. And hence I can just kind of look at the expansion, right? I can look at sum of squares. And so if I do that, I have two terms. The first term just looks at all I did was to there's no cross term. Also here, I guess this one makes right, so neon x outside here. Right, so when you write here that the expectation is with respect to y. Right, so you can break it down into two parts. What is this first term here? It has a special interpretation, right?
Bias.
It's the variance. For a minute I was like, okay, if Zangi is saying that, I think I can do it. 50-50. Right, and what is this interpretation of this term? So yeah, so it is biased, but it's a special kind of bias, right? It's with respect to approximation, right? So it's approximation error, and I'll call it approximation bias because it does contribute to bias. Right, so I'll come to that in a minute, right? Because here I only talked about approximation error and estimation error. I didn't talk about bias and variance, right? Whereas all our previous classes we were talking about bias and variance, right? So the two kind of like are not one-to-one mapping. That's why I want to bring this up, even with simple linear regression, right? So the idea is, right, exactly like what we said here. Right? Even if you had infinite number of samples, you cannot overcome this. Right? If your true model is not linear, no matter what you do, you cannot ever overcome this. So this has to do with the underlying complexity of the function. That's why it's an approximation error. So this contributes to variance, right? But what kind of uncertainty is this? Related to what we talked about in the previous class, right, on uncertainty. We had two kinds of uncertainties, if you recall. We had aleatoric and epistemic. So what kind of uncertainty do you think this is? It's aleatoric, right? So, and that's why different communities have different names for similar notions. So that's why I'm like kind of emphasizing the simple linear regression set. Right? I mean, this overall thing is approximation error, right? Because that was our definition there. Because it was simply asking that with infinite number of samples, how well can I fit the function? Sorry, not that one. Yes. Well, no, this is not approximate. This is just population loss. I'll come to it in a minute. Never mind. Don't ignore that. Right, so this tells me about approximation, but it also contributes to bias, right? So that's why I kind of call it as approximation bias. And this one we can call it approximation variance or aleatoric, because it does contribute to additional variance in a model. Right, so I think that should be approximation error, right? So right, of course, this won't be for an arbitrary W, but for the best one, right? So there is a let's say a W star that minimizes that population loss. Right, so that was this one that would achieve the best approximation error. Right? And so for that estimator, it would be the approximation error, right? So for W star. And this does contribute to approximation error, but then it has nothing to do with the actual W star, right? Because it only has something inherent in the system, right? So no matter what choice of approximation you make, what choice of estimator you do, you can never overcome this. And so that relates to that aleatoric uncertainty. right? No matter what you do, you cannot overcome that uncertainty. Is that clear? So yes, this thing is the approximation error if you look at using W star. So this is W star. Because we are looking for the one that's the best. Is that clear? Good. So far we didn't talk about samples, right? This was infinite number of samples. And now the thing is the same with finite number of samples. Okay, I only am allowed this much space, that's okay. So now I'm going to do a hat of W, which will only look at now right, samples over my finite number of samples. So let's say W hat is the one that is the minimum empirical risk minimizer, right? The one with the minimum. So I'm just going to break this down into multiple parts. Give me a minute here. Right, so the idea is there'll be a part that will be these two terms, right, for the approximation error. Because if I'm looking at the empirical risk, I have to kind of go from incorporating. So what I'm going to do is, in this, I have to compare with W hat, right? So I'm going to add and subtract W star. I'm also going to add and subtract expectation of W x, right? So I'm going to do multiple different terms. So here in this term, I'm going to add and subtract here like we did before, but also we'll add and subtract the term with right W star. So if I have all these, I'll just write down the terms, then we can explain. Right, so essentially because I've added and subtracted both these two terms, right, and now the next one I want to propagate is, right, compare like essentially W star and W hat, right, that's the other term. And right. And instead of just W hat, I'm also going to add and subtract expectation of W hat. Because if you recall about bias, right, we wanted to compare with expectations, right? So that's why I'm going to do additional breakdown. Yeah, so, right, and of course I'm going to compare, there's a typo in the scribe notes from the previous class. Okay, this is hat. Right, so I want to compare expectation of W hat with just W hat, right? So that would be the bias variance breakdown. And then I had this fourth term, which was just this variance term.
I'm so sorry. Could you please, sorry, this expectation of respect to
both X and Y.
Respect to empirical. Respect to what? The measure?
So So yeah, so let me take it back. So I'm gonna use W hat, right? But so yeah, so this is still, I'm gonna look at the expected population risk, but for W hat, right? So yeah, that's why otherwise this is, because I can still ask about estimation error in expectation, right? So that's not empirical. Sorry about that. So W hat is the one that minimizes my empirical risk, right? But I'm going to break down that loss, right, on the empirical risk minimizer. Sorry.
So in the second line, you add expectation of W. I can see it probably.
Yeah, so we are adding and subtracting, right? So we first added and subtracted E of y given x, right? That was the first one. The second one we added and subtracted was W star.
Oh, so that is the expectation of W star. Probably I can see.
And then the third one was expectation of W hat. So you add and subtract three things, right? First is expectation of y given x. Then it's W star. Then it's expectation of W hat. Right, so I mean it's many terms, but I just want to kind of break down, right, how we view the loss for our empirical estimator. Right, and these two we already said contributes to approximation error, right? This first one and last one. So naturally, the other two should contribute to estimation error, right? So the second and third terms are my estimation error, right? So, and the first and the last was the approximation error. Is that clear? Okay, it took us a little bit to make sure all the notation is okay. So far, so good? Right, because the first and the last terms assume infinite number of samples, right? It has nothing to do with finite samples. The second and third term involve W hat, that's estimated using only finite number of samples. So how much error that is incurred there contributes to estimation error. So typically learning theory only worries about estimation error and approximation error, right? Whereas in statistics we are thinking about bias and variance. So you can see here, this contributes to bias, right? This contributes to variance. So that's why, like, this is estimation bias, this is estimation variance. Or in the previous class, we talked about epistemic uncertainty, right? This has to do with epistemic uncertainty. Is that clear? Like the overall empirical loss can be broken down into approximation error, right, plus estimation error. But then each one contributes to bias and variance, right? You can break down your error either as approximation plus estimation error or as bias and variance. So you have like contributions, right, going both ways. Sorry.
Sorry, going back to the middle two terms corresponding to the estimation error.
Yeah.
In like the second inner products, why is the W hat instead of an expectation? Are we taking the expectation over all possible W's, or is that being passed as like a
So expectation over W hat means, right, you could have first of all a probabilistic answer, right? Or you have like the randomness of the samples, right? So you're saying for this procedure, what is this expected W hat?
So the W hat being passed into the L is a random variable.
Right, so it's still a random variable with respect to right, so you still have to average over x, right? So for fixed x, you have some w hat, right? And that could still be random, right? Because y could be random, and or your procedure itself could be random. And that's kind of the notion of bias, if you recall, right? Because we had an estimator, we were looking at what is the expectation of this estimator. Right? And there we just looked at it at infinite samples, so that was kind of, right, accounting for both, right? It was this term, and usually there was no approximation error in what we studied. Right? So in that sense, this term was typically not there because we never dealt with it in our estimation theory. But if you actually make it also not realizable, meaning it's not right in the function class what you're estimating, you have to kind of make that as part of your bias. Right? So when we were studying, this first term was not there, right, in our estimation class. And the variance, we did like further break it down into aleatoric and epistemic. We just put them together. And then the rest was bias. So the other breakdown is this variance has the two components. It's aleatoric and epistemic. So I'm trying to connect different lectures here. That's why it can be a bit confusing, but I want to make sure, right, you connect from different areas and different literature. They're looking at slightly different things, but they're very related. And it makes sense, right? These first two terms are like systematic errors, right? The last two terms is variance. So this is bias, this is variance. And if you make it approximation and estimation error, you switch which terms contribute to it. And if you further look into the sources of variance, there's aleatoric and epistemic. Clear?
When we take expectation of W hat, we assume some distribution of the sample.
Yes.
So it must be centered, so we can cancel out the cluster.
So, so that's, I said typically you can also add like a constant term, right?
Yeah.
But you can, the standard trick is to assume there's a one component of x that is constant. Then I don't need to fit it to constant.
Yeah.
So I just assume that convention to make it easy to break it down. I mean, all this goes through even if you add like a constant term.
Yeah. So for the, what kind of assumption do we need for the sample?
So right now, I guess the only one is, for this breakdown, nothing, right? Of course, for the actual expressions of what they are, you can assume IID, you can assume further ones.
So for this breakdown, even if my sample is always scaled and my expectation of W hat is scaled, I can still have this.
Right. Then you have like a non-zero bias, right? And it can be anything. In fact, we haven't even used that it's minimum, right? It's ERM. We have not used that. This is true for any, so I won't write this. So W hat is any estimator, right? So we haven't used this part in there. Although typically we look for minimum risk in the empirical sense. Of course, minimizing that can like kind of, ask what is the, you can further kind of write down what would be the estimation error for my ERM. Right? That's an added thing to further analyze it. So all I've done is simply break down the loss function for any estimator. Right? So we're just breaking down where the sources of errors come from. questions here? Right, so you can break down your error in terms of approximation error or estimation error, but each of these could contribute partly to bias or to variance. Right, that's a different lens to view the breakdown of errors. And then within variance, there's two forms. There's the aleatory and epistemic. Right, that's the takeaway. I mean, you can do this with any model, right? Not just linear regression. I just showed you there. It's very simple to kind of look at this linear breakdown of errors. Any questions? Good?
Yes. So when we add and subtract inner product W star and X, will that induce a class term?
Right. So you can prove that the cost terms disappear. It requires a few steps.
Okay.
Yeah. Yeah. No, I didn't touch it, but you can verify that. I guess, of course, adding and subtracting expectation, we know that it cancels. So for others as well, we can show. Good, good. So that's the main takeaway, right? Like, typically the errors come from so many different sources, and that's why it's hard to disentangle what's happening in a complex neural network. Because is it really one of approximation? I mean, should you make your network bigger or smaller? I mean, typically you want to keep making it bigger, right? But the idea is, as you make it bigger, you could suffer a bigger estimation error. Meaning with your small data set, it may not be enough, right, to train a big network. Otherwise, you would all be just training billion parameter networks for everything, right? So, and of course, there's a computation cost to it as well. That's another aspect. But the idea is this balance of estimation and approximation error. Because, again, if you look at the linear model here, right, your estimation error can be controlled, right? Because you can have the ability to estimate efficiently. It's a low complexity solution, right? So you can estimate it well. But you could pay a huge approximation error. Right? And that's why we also don't use linear regression for all symptoms. Right? To fit image like pixels, we can't use this. Right? It's too huge an approximation error. And that's why in practice it's the balance between the two. Good. Any questions still about the breakdown?
How do you control the approximation bias?
So you mean this one, right?
Yeah.
So exactly. So it's like the question is, how close are you to this true base optimal one? Of course, you.
Depends on the complexity of the model.
Yeah, of the underlying one. So it depends on what assumptions you're making, right? If your assumption is this is, say, a linear function, this expectation of y given x, the base optimal estimator is linear, then this is 0. Right? If this is non-linear, no matter what you're doing, you have to pay this price with a linear estimator. Right? So linear regression doesn't solve all our world's problems. So that's why we need to go to nonlinear estimators now. Before we jump to neural networks, I just want to give a quick primer on kernels, kernel models, right? And why kernels, why not, and then go to neural networks. How many of you have seen kernel theory, worked on kernels? Okay, a few. Not all, so which is good. I will. Maybe I'll keep this. Yeah, so, right, so it's not, now we cannot use linear regression all the time. So we'd like to have a non-parametric setup. So if you recall, during the first part of the class when we went into depth on statistical inference, I said we are mostly limiting to parametric estimators, but the real-world problems a lot of times require non-parametric ones, right? So parametric means it's some fixed function family, right? The distribution, right? Let's say the exponential family we studied a lot, right? It had like a certain parametric form in the form of exponential. But then if you don't want to make those assumptions, how do you design your estimators or detectors? And the simplest kind of extension is to say, I will, instead of thinking about doing linear regression directly in the input space, I could think of it conceptually as doing linear regression in some feature space. Right? So if I could transform my nonlinear data to a space that is linear, I can still use all the linear regression or linear theory, right? Linear model theory. And that's the whole kind of intuition behind kernels. The idea is I'm gonna transform my input X into some feature map, right? So these are called feature maps. Or feature embedding, because I'm also embedding X into that space. And to just give you a simple intuition, you've probably seen it in some maybe online videos or something, right? So there's kind of these kind of nonlinear, these are positive examples, meaning these are positive class. This is, right, the negative class for binary classification, right? So if I try to look at, let me do it without this dots. Let me try to draw more clean. Right, so let's say I have a binary classification problem. I want to do that whether there's a cat or not a cat in images. Right, so if I just look at, say, in the space of pixels, okay, let me draw it with just shapes. This is how I'm going to do it. Okay, so I just want to show something nonlinear, right? So there's one class that is, having this nonlinear manifold shape, and this is the other class. If I try to do a linear classifier, I can never separate the two, right? It's, so these are positive classes, negative class. Is that clear? So I have these examples I draw. If I try to do linear classification, I'm bound to make errors, right? Because even in this kind of case, right? This, of course, here I made it separable, but you can see, right? I kind of will run through some errors when I try to do the classification. So on the other hand, if I transform it into some feature map where, right, it's all linearly separable, then I can just use my linear classifier, but now in this new space. Right? So the intuition is very simple. Just in the input space, linear classifier is bad, right? It incurs a bad approximation error. But if it could just do the transformation to nonlinear space, in a nonlinear way to a feature space, there, hopefully it becomes linear, right? I could try to find one where it is good. It's linearly separable in the best case. And that's the whole intuition, right? So when I'm dealing with highly nonlinear, complex functions, right, between the input and output, between X and Y, if I can do this intermediate transformation, where if I apply now either linear regression or classification on this feature map, it's still a good performance. The approximation error is small. And so that's the intuition behind using this feature embedding. Right, so the question is now, how do we come up with that, right? So right now it's just intuition. So how do we come up with feature embedding? So what the kernel theory says is, right, like you can think of this feature embedding as in some potentially even infinite dimensional space, right? So I'm never going to explicitly tell you what this feature embedding value is, right? I can never evaluate this directly. But what I can do is compute inner products, right, between different feature maps. And that's called the kernel matrix. So I'm going to look at, say, one image, another image, and I will tell you what is the kernel function between the two images, or similarity function. Right? So the intuition is you have two pictures of cats. Hopefully their similarity mapping is close, right? Whereas you have a cat and a dog, they're further away. Right? So you're only measuring like closeness between samples rather than the actual value of the feature embedding. Right? This potentially it's infinite dimension. And so that's the way to kind of get around it, like I can implicitly just measure similarities. And the intuition is, this is also potentially something you can ask human to give you, right? In different kind of experiments, people have tried to, do human experiments of how people perceive which images are similar, which ones are not. Right? So you can get sometimes even annotations like that or information like that. So it makes a lot of sense to think about just similarities and not worry about the actual value of feature embedding. And so there the assumption is, right, the function, right, to express now my output, this f of x, right, is right, some combination. So this is in general like feature embedding, right? So any function I express, right, there is a Hilbert space. Won't go into all the details, but the main idea is there are some basis functions, and I can express, right, my map in terms of these basis functions. I mean, typically they're also infinite basis functions, right? So the summation could be, let's say this is k of them. So instead of summation, I could just kind of have an infinite one, right? So, I mean, still kind of countable. So it need not be finite. Potentially, there are infinite set of basis functions, and I can express any function, right, with this. But in a linear combination, right? So all I have to do is look at linear combinations of basis functions, and hence, I can do now. If I knew what the basis function is, this is just again linear regression or linear classification, right? So nothing has changed. The only thing challenge is if this basis function is in some infinite dimensional space, I cannot directly evaluate it, but I can do it through inner products, right? So that's why you kind of look at the kernel matrix of your data and try to come up with what is the estimation of these linear coefficients. So a lot of like linear theory goes through almost directly, but the idea is you now have some basis functions on which you want to regress upon. And so if you're looking at like the RBF kernel, which is called the radial basis function, as an example of this kernel function, right, that just says a simple way to measure closeness, right? It just says that it is just, right, exponent, it's just close in terms of, right, a Gaussian function. And similarly, you can come up with other kernels, right? So the kernel theory is kind of based on assuming some kernel function, right? So you still haven't kind of gone away with that, completely, right? Because even though this is non-parametric in the sense we are not making a fixed distribution choice, we are still making a choice of kernel. And this is typically the reason why they don't work that well on images, because why is this a good similarity measure for images, right? Maybe it's not. So that's one of the shortcomings, right? I still have to choose what my kernel function is. Right? And the other shortcoming is, like this basis is typically it's infinite, right? So it's what we call like fixed basis and not adaptive, that's learned from data. So there is fixed and adaptive basis. So again, this is more signal processing terminology than learning. So again, it's kind of from one community to another, it's different. So fixed basis in learning theory is referred to as kernel theory, right? Use of kernels. Adaptive basis is neural networks. That's one way to get adaptive basis. There could be other ways. So that comes more from signal processing theory. But the idea is if you're looking at a kernel framework, you get a lot of benefits similar to linear models because it's still linear in this feature embedding space. But the shortcoming is you have to choose what your kernel function is, right? Say something like RBF means it's kind of smooth, right, in your input space. So you're making that choice. And once you make the choice of your kernel function, your basis is fixed, right? Your basis is completely determined just based on your kernel function. So you have no way to change your basis. Whereas if you can adapt the basis based on your data, meaning you're also learning the basis from data, right? That's called adaptive basis. A neural network gives us a way to also get adaptive basis. So essentially what we are doing in a neural network is also learning basis functions, right? That is the difference from kernel theory going to neural networks. Any questions here?
I don't know how neural net doing that, but generally, do we have a way of mathematically writing how we can select kernel, how we can move in a kernel space? I don't know. How
So
you can.
the kernel is usually a fixed choice, right?
That's right.
So, and that's why it's, it's again kind of like the graduate student research, right? So that's the hyperparameter selection. Of course, within a kernel choice as well, there is the choice of, like in this example, this is called the bandwidth, right? How do you want to kind of scale your distances? So there are choices, right? So this, and even in neural network, there are choices, right? Like kind of the holy grail of automated ML is you give no input whatsoever, it picks everything, right? But that's never going to happen unless we have infinite computations or we completely understand the domain, right? So something has to kind of be there. So we have to make choices. But the choices are different when it comes to kernels versus neural networks, right? So in kernels, the choice is what is the kernel function, what is the family of functions, and within that, what are the choice of parameters within the kernel family. Once I do that, I can crank the wheel of converting all my linear models to now kernel models, right? And this is called the kernel trick because I just have to always evaluate, right, through these inner products. So I can find these coefficients without ever explicitly, right, evaluating the basis functions or feature types.
So, for example, as you mentioned, for example, this needs some sort of smoothness, right? This one. Now, assume that I have some idea, some of it might be this, or some other kernel that doesn't have, for example, the smoothness doesn't. Then is it possible to consider, for example, 10 of them and then kind of select, randomize it? I don't know.
I mean, that's what people do in practice, right? They try one kernel, they decide this is not so great, they try another one. And there is domain knowledge built in, right? So for the functions that are not smooth, there's something known as Mattern kernel where, it assumes like kind of derivatives up to some order is bounded, right? So you can use that choice. If you're looking at strings, if you're looking at text, comparing similarity between strings, that's called a string kernel. So there's been a lot of extensive theory on, for specific domains, what is the choice of kernels, right? Similarly, as we see now with neural networks, different architectures. If you're doing text, should you do transformer? If you're doing images, should you do convolution? Right? So similarly, even in kernel theory, there are specific choice of kernels. So that does help a bit, right? But the main downside, I would say, is the aspect that you're limiting to fixed basis, right? Because the only way you can control your basis is through the choice of kernel function. So you don't have as much ways to learn from data as in adaptive basis setting.
Now, for example, what I meant, probably I have to rephrase it. Let's assume that I have 10,000, so many kernels, somehow parameterize it, and just run gradient descent even over that space. I guess it's
in a way that's meta-learning, right? So meta-learning does the same, not with kernels, but with neural networks, right? So you can kind of always, also do gradient descent in nested loops, right? Typically you hope you can do something better than that, but that's always a choice. But the idea is, again, how do you parameterize, right? Kernels of kernels. So, people have, by the way, this is the simplest setting, people have come up with nested kernels, right? You can nest one kernel in another. For instance, or you can also think in terms of wavelets, right? Like wavelets are hierarchical. Polynomials, right? You can do it in a nested way. So because you can go from order, say, k polynomial to order k plus 1, right? You can nest this. So there are ways to think of nested kernels. In that case, right, it now looks like a deep neural network, right? You have multiple layers of composition. But again, the difference there is, if I'm adaptively also choosing what my basis function is, it's adaptive basis, or a neural network. But if I'm not making that, that's a fixed basis choice. So, right, so I can use either setting.
So for anything, we have this adopted, we call it neural net. So neural net is the term that we use for.
So typically, yeah, so now when we go to neural network, right, so typically it means there are layers of neurons, right, and we are learning function mappings from one to another. But even that's kind of changing, right? We have also, say, ordinary differential equation solvers within layers of neural networks, right? And it's not even layers, it could be other. So more generally, I think of it as a transformation between input and output, right? And I'm expressing it in terms of some primitives, right? Some operations. I'm learning how to put those operations together, compose them. Right, so that's, to me, the neural network in its most general formulation. But typically the ones we consider is simple, matrix multiplication operations with some nonlinearity. Right, so what we call fully connected net, that is the most ancient kind of, or the one that was studied first. Right, and the shallow network is just one layer, right, of that setting. So which means it's this setup. But the difference is learning both the coefficients and these basis functions. And the way we are choosing these basis functions is another layer of matrix multiplication with some nonlinearity like sigmoid or rectified linear units. So we'll now look into how to think about expressivity or approximation error of such networks. Any questions so far? Right, so actually I can just erase this because all these stand, right? The only difference is we won't be thinking of fixed basis, we'll do it adaptive. So I will still use this. And instead of infinite basis, we'll have typically a finite neural network, right, of finite size. So let's say there are k units in the first layer, right? So these are the k units. And instead of this being arbitrary basis functions, let me call this as, right, sigmoid. So let me say, it could be sigmoid, could be relu, it's some nonlinearity, right? So sigma of, say, some parameter c, right, could be either a relu or a sigmoid, right? Or anything else too. And so what the first layer does is we are doing matrix multiplication. Again, there could be also a constant term. I'm always absorbing the constant term. So that's my first layer. And then in the second layer, right, I'm going to again do another multiplication. And so I'll just write it in this form. Right, this is my shadow network. So here we are learning both W and C. That's why it's adaptive basis. Right? I'm adapting what is the set of neurons I want in my first layer. You could think of it as the basis to represent the classifier, right, or my function. So the question is, I guess you've heard of the expression that neural networks are universal approximators, right? Meaning any function, right, on the real line can be expressed using neural networks of some arbitrary size, right? So in the limit, it could be infinite size. But the idea is if the function has, right, bounded complexity, it's some bound on what was the size, right? Because the idea here was we had now, say, k units in the first layer. So there's some size of x, right, whatever that is. And in the simpler setting we are looking at, y is a scalar, right? So if it's binary classification, you just need to compute one function, right? So we'll look at that simple setting. Of course, in general, y could be, vector or even more complex objects, right? So that's the simple setting we are considering. So you can easily extend from binary to multi-class classification, right, in terms of approximating. But we'll just look at the binary case. So the question is, how should you choose the scale, right? So what is the intuition of how large or small the case should be for different functions? And it scales, of course, also with x, right? If you keep looking at a larger input, you do expect more units, right, to be there. But also it depends on the complexity of the function. So if the function is constant, right, it's trivial, all you need is just one unit, right? So if the function, is literally just a relu, you just need one unit, right? So the question is, how do I measure complexity of the function? Again, this is oracle, right, because I don't know what that function is. If I knew, I could have just used that. But the question is, can I tell what this approximation error is for a finite size network? If I pick a network of size k and I tell you what the true underlying function is, can you tell me what the approximation error is? Right? We'd like a bound on this. And that's what this paper by Barron, right, in the 80s characterized. So the main result is that this approximation error essentially scales as 1 over k. Right? So if you have k units, the square approximation error scales as 1 over k. If you just look at, of course, I didn't say with respect to what, right? I have to look at expectation on x in some domain, and the domain will look at as some ball of fixed radius r. So I'll call this r. So I'm going to look at, so let me call this f hat, right? Because there's true function f, and this is my approximation. Right? I'm fitting this to the neural network. So I'm going to look at all bounded input in some ball. So this is nothing but, let me just do it directly. So there's some norm, and I'm going to look at like all bounded x, right? So again, this is a technical detail, otherwise I can't evaluate my integral without it. It could also have some probability measure, right? There's some probability of x. So this is nothing but p of x dx, right? If it's, again, integrable or the limit measure. So I can, this is my approximation error, right? Because this is infinite samples, it's saying what is the best possible neural network that can fit to my underlying function. And the balanced result says this is something like there's some constant divided by k, where k is the number of units in a shallow network. And the idea is this C is, let me directly write this here. So it depends on the radius, of course, right? So if the radius is small, you expect this to be small, right? So that's why there is this here. And there's also a function that depends on the complexity of the true underlying function. I call that CF.
This holds for any nonlinear, for example, that you put on your node, any value, whatever, right?
Yeah, so we'll mostly deal with sigmoids, bounded ones, but there is no extension after Barron to also do it for errors. So it's fairly weak conditions to hold nonlinearities.
But for this, it's a sigma. But for this, it's a sigma.
Yeah, I mean, in Barron's result, yeah, for this it's a sigmoid. I think the results only maybe slightly change. It's still 1 over k.
Is the proof hard?
So let me give the intuition so that so first, right, so what is the main intuition? Before we worry about sigmoids, if we instead had say sinusoidal units, right, so both sines and cosines here, you can relate, right, this fitting to essentially what is the residual in your Fourier spectrum. So if you've done signal processing, this is the time it will be useful, right? Because if you recall, right, your Fourier expansion, right, in general for an arbitrary function, it's infinite Fourier expansion. But you can ask, if I only look at the top frequencies, right, in my spectrum, how much is the residue, right? What's left out? So the CF, in fact, is directly given by that. It's looking at, right, what is the spectrum of your residue, of your derivative, right? Because that tells you what is the right sensitivity to of your function in the Fourier spectrum, right, in the Fourier space. And so the CF, just to first do the definition, is looking at this. So it's in terms of the magnitude, right? I mean, you're taking the norm, you're taking the magnitude. But the intuition of where this comes from is, if I'm looking at my Fourier expansion, right? So this is recalling your Fourier series, right? You have this. This is just Fourier transform, right? If I look at the derivative of my function with respect to input, not with respect to weights, we are not doing that properly. This is like the sensitivity, right? It tells you if I have high frequency content, if you recall your Fourier theory, right, the derivative will be large, right, because it gets scaled up by the frequency. So this is now nothing but j omega And what the CF is doing is just looking at the magnitude of this. Right? So if you look at the magnitude and you come up with the bound, that's just this. And that's the intuition, right? So all this goes back to signal theory, because the idea is if you have now, right, very fast varying non-smooth function, that's hard to approximate. If I have a smooth function, it's very easy to approximate in the Fourier space. Right? In fact, this is just one sinusoid. Right? This has very high frequency content. And so the more the high frequency content is, right, the sensitivity is more. And the intuition is you pay a higher price in approximating high frequency content. Right? And this is a bound, this is an upper bound of what it can be. And so the theory solely relies on the fact that if you start with just sinusoidal units, right, this is the error.